Okay, mic check. Fantastic. Okay, so we are back again for more exciting Atari 5200 programming. Now, just to warn, I'm actually a little bit sick today, so I don't know how long this stream's going to go. I may end up having to bail out just a bit early. We'll see how it goes. But I figure this is the second week of this series, and I figure we'll start off with this week is correcting the mistakes from last week, which I have a feeling is going to be a recurring theme. But we'll see. So last week, I attempted to just get a basic 5200 game up and running, but I was running into a snag. For some reason, something was going wrong. I couldn't get anything drawn to the screen. Now, a couple hours after I ended that stream, I was looking at the code and I figured out exactly what I did wrong. And I want to go over that now because it's important to understand what I screwed up. Because what's most embarrassing about it is that I didn't follow my own advice when it came to this stuff. So here's where the issue was, and I've already fixed the code for this. So when I first started up the system, or at least when the cartridge first took control, the very first thing I did in the code was I cleared all the RAM. That was a problem. So if you go back to the first video I did, which I've posted on YouTube, you can find it there at my Phasercat Games channel. Just, find it. It's not hard. One of the things I mentioned when I was going over the 5200 hardware was that page 1 of memory is the processor stack. And I said, don't touch page 1. Well, I should have followed my own advice, and I was unthinkingly touching page 1. So the reason this is important is because I was clearing memory pages with this subroutine right here, clear page. So when the processor jumps to a subroutine, it needs to store somewhere a means of getting back to where it came from. That's called the return address. And the way it does that is that it puts the return address onto the processor stack. So when I was clearing the memory, I eventually got to, let's clear page 1. So I would do a jump to subroutine to clear page. Here's clear page. And at this point, when we enter this subroutine, the return address, being this instruction, is currently sitting on the stack somewhere on page 1. And then this routine just went ahead and cleared out the whole stack, which wiped out that return address. And at that point, everything just went crazy. So, and for the record, once you hit this RTS instruction, return from subroutine, the processor goes to the stack, pulls that return address off, and resumes execution at that address. But since I had blown away the stack in the subroutine, that got bad. So the way I've done the code now is we start at 3F, which is the last page of RAM, clear the page, compare to 2. I stop at page 2. We're not doing that. And if it's page 2, we jump here and we say we're done. Now, one thing I didn't put in here is a page 0 clear, which I really actually should do. So I kind of forgot to do that. So let's go ahead and throw that in there now. So we're going to do a loadex, do a page 0 clear independently. Because I just don't touch page 1. Don't be an idiot like I was. And then we clear the 3 chips. I think this is GT, ANTIC, and Pokey. So this works. Now the other thing I wanted to correct was when I was demonstrating how to do the 5200 boot up screen with the title and the copyright date, I kept screwing it up, so I went and figured out exactly how it's supposed to work. Now what I had mentioned was that this byte right here, BFFD, if this byte is FF, it identifies to the BIOS that this is a diagnostic cartridge, and it skips the cool Atari boot up splash logo. But where I kept running into problems was trying to set up the copyright date. And what I didn't realize is that this byte is where the second digit of the copyright date goes, for which FF is not a valid digit for the copyright date. So this is the second byte of the copyright date. So you have a 20-byte cartridge name, a byte for the first digit of the date, and the second. Now, here I'm doing the digit as 5 followed by the actual number. And the reason for this is because the actual character code for a digit is hexadecimal 1 followed by the digit. So 17 is the character code for the 7 digit. But the graphics mode that's being used here for this boot up screen, the top 4 bits of each character code control the color. So if we want white, we need to set one of those bits. So that 5 includes that color bit. So now if we run this, we'll get that boot up screen, and it'll look correct and nice. And there it is. And then we get a white screen. This is the white screen I was trying to get before, but I screwed up. So there it is. Now we're on track, and we can do some more interesting things. So before I go a little farther, let's talk a little bit about that white screen. So why is that screen white? That screen is white because I put the value 0E into here, color background. So I want to talk a little bit about color codes. Now, if I go to my hardware file, I have a little color code guide down here. And you see here, 0 is gray. So the way the color codes work on the 5200, and I think these are the exact same color codes as the 2600, but I may be wrong about that. Double check me. Is that the nibble, the most significant nibble, is the color. The right nibble, the least significant nibble, is the brightness. So you have 16 colors, and that's these colors listed here. Notice there are 2 blues. They're slightly different blues, I think, but there are 2 blues. So the leftmost nibble is the color code. The rightmost nibble is the brightness. However, in most graphics modes, the least significant bit of the color code, the 1 bit, is ignored. So color 1E or 0E, which in this case is white, it's gray at maximum brightness, which is white. 0E and 0F are the same color because that lowest bit is ignored. I usually go with the lower number. You can use either one. It doesn't matter. I usually go with the lower one. But let's just change it, for example. Let's do here, F is light orange. So what we're going to do is we're going to make this FE. So this is going to be the brightest value of light orange. And we'll see what that looks like. Oh, I forgot to disable that. I should disable that, so you don't have to wait for it every time. Okay, so that is... I think I see a very faint orange tint to that. It's kind of tough to see. Let's make it not quite as dark. So we'll tone the darkness down to, say, 6. Tone the brightness down. Oh, wait, I want to kill that boot screen. So we get rid of all that nonsense. We change this back to FF. Okay, so there we go. So there's kind of an orangish color. So that's how color codes work. Your first nibble is the color, and the second nibble is the brightness. And as I said, the lowest bit in the code is ignored for most graphics modes. So F6 and F7 are the same color. Wait, no, it's the other way around. No, that's right, yeah. F6 and F7 are the same color. Now, there are some really odd special modes, which I've never used before, but I plan to use in my next game, that have a full 256 colors, where that last bit is a factor. But maybe I'll play with one of those at some point during this. I've never used them before, and I do intend to use them for my next game. And speaking of games, a couple days ago I released Robin Banks, my newest 5200 game. It's complete now. You can go download it from my website at phasercat.com, and that comes with a complete source code. So you can download that, play around with it, see what you can do with it. Okay, so I'm going to change the background color to black, which is just 0. And we're going to play around a little bit with ANTIC and Playfield. Now, I started putting together a display list here, but I'm going to get rid of this display list. We're going to do something else. We're going to play with text mode. So, mode 2, ANTIC mode 2, is 40 column text. So, this byte right here says, hey ANTIC, give me a row of mode 2. And this 4 means, and I'm going to give you an address to start reading data from. And the address right here is 0020, So, that's where it's going to pull its graphics data from. Now, the way that color works in... let me get rid of these. The way that color works in this mode is a little bit weird. And I have to look it up every time I do it. And I actually have a page open on my other monitor with the instructions to do this. So I actually get most of my information from Wikipedia these days. If you go to Wikipedia and just search for Atari ANTIC, you'll find a page that breaks down all this stuff in fantastic detail. And I'm on that page right now, and I'm looking at the stuff for Mode 2. Okay, so on Mode 2, the background color is actually used as a border around the outside of the screen. So let's make a visible border just to show this off. So we'll make color black, make the background color the white color again. And this should show up as sort of a border around that one mode line of Mode 2. Okay, and you can see it there. You see that black line going across there? That's my one mode line of Mode 2. So that is a single line of Mode 2. That's how tall it is. It's 8 scan lines. So I've told ANTIC, put a line of Mode 2 here. Now, it's reading the data that goes in that mode from address hex 2000. But right now, that's all zeros. We zero out the memory. And 0 is space. It's a character code for space. So there's just nothing there to display. Now, the way that colors work in Mode 2 is a little weird. Okay, so in Mode 2, and I'm going to change this background color back to black. The color of the text is like a combination of 2 different values. So you have, let me see if I can understand this. Okay, it says the luminance value from Playfield 1 based on the background color value from Playfield 2. So by writing this to both, okay, so color 1 is color 1. The Playfield has in this mode 3 colors in addition to the background. Colors 1, 2, and 3. So I'm going to write this to both colors 1 and 2, and it should give me white text, I believe. Oh, I need to actually put text there. No, it didn't. Okay, I screwed that up. I always get this wrong at first. Actually, I'm not quite sure why it's displaying that, but we're going to go ahead and put some actual text at that address that it's trying to draw at, which is PF2. So I'm going to put some text here. We'll put a label on it. We'll call it Hello World. We'll do it the traditional programming Hello World application. So we're going to put byte, and I'm going to put this all in lowercase. I'll explain why in a little bit. So what we're going to do is we're going to copy those bytes to address 2000. So here's how we're going to do that. We're going to load Y with the length of that string, which is 11 characters. Well, actually, we'll do 10, because it can be offset of 10. 10. Then we'll make a label called text loop. We're going to load... No, so hello world is a label that resolves to the address of that string. So we do hello world indexed by Y. So it's like reading into an array if you're familiar with other programming languages. And then we're going to store that at 2000Y. And then decrement Y. And until it becomes negative, we branch back and do it again. So this will copy that string into address 2000, which is where the ANTIC display list is looking for the text. And we'll see if we can get this to display here. Okay, so something's still not quite right here. You know, I'm going to look at I always screw up the way color works in this mode. It's really confusing. So I'm going to go look at the Robin Banks code to figure out how I do this, because I don't remember. Title screen should have it. Okay, so I can put 0 into color 2, and then 0E into color 1. Okay. You know, I'm not sure why I was getting what I was getting. but so the way color works in this mode is just really weird. This is not how the other modes work. This is an unusual case. There we go. Oh, I forgot. Space is not right. Space is the wrong character. But you can see here that we've got some text. So this is mode 2. This is ANTIC mode 2. And I'm going to correct that little problem there. So instead of put a 0 there. Okay. So the problem we're running into here is that the ASCII character codes that the assembler outputs don't line up with what the 1500 expects. So you need to correct them sometimes. And the reason I did all lowercase here is because lowercase letters do line up. So lowercase ASCII is also lowercase on the 5200. They're the same character codes. I think every other character needs to be offset by 32. I think you need to subtract 32 from it. Now, there are a couple of ways you can go about doing this. One way is to actually put the proper character codes into your binary, which means that instead of a space here, I put a 0 like this. An alternative way is to write a subroutine that will take one of these text strings, do the necessary conversion, and put it where you want it. And in practice, I typically use both of those methods for different strings. The advantage of having the subroutine is that it makes the strings readable in the text instead of just blobs of binary data. But there are some other cases where I just have large paragraphs or something that are just in binary. So it depends. You know, you do whatever works for you. But I don't plan on doing a whole lot with text here, at least not initially. So I don't think I'm going to put too much effort into text processing. But text is a bit of a pain, to be honest. But this is mode 2, 40-column text. This is a single mode line of mode 2. So let's look at that display list again, just as a bit of a refresher. So these first 3 lines, the $70, this means skip. Each of these $70s here means skip 8 scan lines. This is the overscan area at the top of the television screen, which is not necessarily going to show up on every TV. So you skip 24 scan lines, and that brings you back into the guaranteed visible area on every television. So almost every ANTIC display is going to start with 3 $70s. And then this is our one mode line we're requesting. This is mode 2, which is the rightmost nibble. The 4 is a bit. The leftmost nibble are 4 control bits. And this particular bit means the next 2 bytes in the list are the address I want ANTIC to start reading the Playfield data from. And this is a little endian, so least significant bit comes first. So we have 0020, which is address hex 2000, which is where we copied the text to. So essentially what ANTIC is doing here is it's going to address 2000, and every byte it reads, it treats as a character code. And it goes and it looks it up in the character set and then displays it on the screen. Now, we told ANTIC where the character set was during the initial system setup, and that's this right here, CH base. This is a register in ANTIC, and you give it the page number that the character set resides on. And here we gave it F8. Now, F8 is a page in the BIOS. So unlike the 7800 or the 2600, either one of those, the 5200 has a built-in character set. And those other 2 consoles, you need to create your own character set and store it in your ROM. So you lose space to that. You have to make up your own character set in your ROM, which kind of stinks. But the 5200 has this built-in one right here that you can use for most of your stuff. And that's called mode 2. Now, there are a couple other variations on mode 2 that I think are like 3 and 4 or whatever. Like one of them has descenders for characters like lowercase g that come down. You know, it could go below the line. I think mode 2 just moves that up. In fact, let's look at it. I've never played with the descender modes, and I don't really intend to right now, but just to explain what I'm talking about, we're going to change that O to a G. So you can see here, once it comes up, is that the G is not very low. Like, it's a little low. It's down one line. But there is another variation on mode 2. I think it's mode 3. That allows descenders, and in that mode, that G would appear lower. But I've never played with that mode. I've never really felt much of a need to. But there's mode 2. Interesting, huh? So that is an example of Playfield. And that is just one of many Playfield modes. And we'll play with some of the other ones in a bit. But before I go much further, I would like to talk a little bit about player and missile graphics. And I think that's kind of going to be the focus for this particular video. We'll see what we can do. And I'm going to leave this display list as is. It's fine. In fact, I might even leave the message in there just to demonstrate some stuff. So let's talk a bit about players and missiles. So when it comes to graphics on the 5200, you have the following things at your disposal. You have the playfield, which I just demonstrated a little bit, but there's a whole lot more to the playfield than just text. And then you have the players and the missiles. So there are 4 objects called players, and there are 4 objects called missiles. And these are collectively referred to as the sprites. And they're objects that are independent of the playfield that you can place on the screen to move around. Now, the advantages of the sprites is that they are relatively easy to move them around. Moving things around in the playfield is rather difficult. Sometimes you're forced to do it, and these are what are often referred to as software sprites, where you actually build sprites on the playfield. As an example of this, if you go look at one of my games, if you go look at Real Sports Curling, which I'm not going to show here, but if you can find videos of it online, in that game, the rocks that slide down the playfield are actually part of the playfield. Those are playfield sprites. And the reason I had to do that was just because of quantity. I needed to be able to put 16 rocks on the screen, and you don't get enough objects for that. But let's go back to the sprites and the objects. So the players, the 4 players, are each 8 pixels wide, and they're a single color. Now, notice I didn't say anything about height. So the players and the missiles as well are effectively the height of the entire screen. So you can imagine a player as a column of 8 pixels that goes from the top of the screen to the bottom of the screen. So there's no real vertical position. And it's one color, so the pixels are either on or they're off. Now the missiles are 2 pixels wide. And each player has an associated missile. So you got player 0, you got missile 0, player 1, missile 1, and so on. And under normal circumstances, a player and its missile are the same color. There is a mode called 5th player mode, which allows you to select an independent color for the missiles. But that color applies to all 4 missiles. And the intent being, this is why it's called 5th player mode, and I talked about this a little bit last week, is that you can take those 4 2-pixel wide missiles and put them right next to each other, and now it's like you have another 8-pixel wide player. And I've used that technique in 2 of my games so far. Yeah, 2 of them. But let's get into the players and the missiles. So there was some setup involved here with the players and the missiles. And the 2 most important things are, if I can find them, DMA Control. So DMA Control, there are several bits I'm setting here, and I have to pull up a diagram on Wikipedia to figure out what all these bits mean. But among these bits are the bits that turn on ANTIC's player missile capabilities and allow it to actually read the data that it uses for players and missiles. I believe that graphics control, I believe this bit also enables players and missiles from the GTIA side. So you need to make sure these are both set correctly. And then there's PM base. PM base stands for player missile base. This is where you tell the ANTIC chip where to get the data that it's going to use to display the players and the missiles. Because if I can segue into a little bit of theory here, the 2600 also has players and missiles, and it has another object called the ball. But the TIA chip in the 2600, again, only knows about a single scan line at a time. So it has registers that contain the bit pattern for each object on that one scan line. So you need to change that bit pattern, scan line by scan line, all the way down the screen. The GTIA works the exact same way. But what ANTIC does is ANTIC takes the data you give to it and just continuously feeds that data to GTIA. So what happens effectively is that each object occupies a page of memory. And ANTIC starts at the top and goes all the way down and just feeds that data into GTIA, scan line by scan line. And we'll see that here real quick. So what we're going to do is we're going to start by making a simple hardware sprite. We're going to make player 0. We're going to put them on the screen. So how are we going to do that? Well, first we're going to make a white square. I think a white square will be great. So here's what we're going to do. We're going to take this color 0E here, which is white. In addition to storing it at Playfield color 1, we're going to store it at color PM0. Stands for color player missile 0. So now player missile 0 is now white. Then we're going to, what we'll do is after the text loop, we're going to position the player. So let's put it at, I don't know, we'll start at 80 and see where that ends up. I don't remember where a lot of these values end up. So I'm going to write this to a register called HPOS P0. Stands for horizontal position player 0. Now, as I mentioned before, there is no vertical position player 0 because the player doesn't really have a vertical position. It's the entire height of the screen. So what we're going to do now is I'm going to turn on all the bits in a few locations. So now we told ANTIC up here, and we set PM base, that the player missile data was on page 10, hex 10. So here's the way this is laid out. ANTIC ignores pages 10, 11, and 12. It ignores the first 3 pages from the location you give it. And I suspect the reason it does that is because it allows you to place the player missile base at page 0. Because if you did put it at page 0, you would want to skip the first 3 pages. Because page 0 is special and has reserve space on it. Page 1 is the processor stack, and we've already learned you don't want to mess with that. And page 2 also has reserve space on it. It has the jump table for the interrupt vectors. So if the player missile base didn't skip the first 3 pages, you wouldn't be able to put it at page 0. And I'm pretty sure that's why it works the way it does. But I usually put it at page hex 10, and there are some limitations on where it can be placed. But hex 10 is usually good enough. That's usually where I put it. So that being said, so PM base plus 0 plus 1 and plus 2 is probably the more accurate way to put it. Those pages are ignored. PM base plus 3 is the data for the missiles. Now we're not going to do missiles, yes, we're going to ignore that. But PM base plus 4 is the page with player 0's graphics data on it. So I'm going to write these FFs to some locations on page 14 hex, because that's where player 0's data is. So let's put it to, oh, I don't know. We'll do 1480. Whoops. What did I hit? Okay, I don't know what I did there. It's the joy of Vim. Sometimes you miss a key and just weird stuff starts happening. So we'll try that again. So do 1480. Now I meant to copy this. We'll do seven more rows. So 1480. 1, 2, 3, 4, 5, 6, 7. Okay, so if all goes well, we should now see player 0 somewhere on the screen. So let's see what we get here. We don't see him. Why do we not see player 0? Oh, because I wiped out the HPOS P0 setting. Which brings me to an important point I would like to make as soon as we actually see player 0 here. There he is. Okay, so that little white rectangle there, that is player 0. Now, one thing you might notice, well, maybe you notice, I said that the player was 8 pixels wide. So each byte has 8 bits. So each bit corresponds to 1 pixel. So if you look at the code, what I wrote into the memory that represents player 0 was FF, which means all the pixels, all the bytes are set to 1. So this is doing all 8 pixels across for 8 rows. Now you'd think that would result in a square, right? 8 by 8? Well, it doesn't. And the reason it doesn't is because pixels on the system are generally not square. They're more rectangular. And they're rectangular in almost a 2-to-1 ratio. It's actually slightly off. I don't remember what, it's like 1.92 to 1 or something like that. But it's basically 2-to-1. So if you want a square, you need twice as many rows as you have columns. So a square player is going to be 8 by 16, not 8 by 8. So let's put in 8 more rows here. And this is an incredibly wasteful way to do this, but I don't care. So 8, 9, A, B, C, D, E, F. All right, so there's something much closer to a square. Now, 8 by 16 is usually a pretty good size for a player. Robin Banks, the player and the cops are all 8 by 16. But that's how you get a player on the screen. Now, let's just go over a little bit about what's actually happening here. ANTIC is going to page hexadecimal 14, page 14. And it's starting from the top of page 14. And as GTS spits out scan lines, ANTIC keeps setting the pattern for player 0, the bits that are on, the bits that are off, all the way down the screen. It goes byte by byte through that page of memory. So every byte on page 14 is 1 row of the player 0 sprite from top to bottom. So I put 16 FFs in a row, and this is what I got, because there are 16 solid rows, and it happened to land right there. So the way I usually conceptualize the vertical position of a sprite on the system is, what is the top row, the byte of the top row, like the address within the page, and that's the vertical position. So let's mix this up a little bit, though. So what I'm going to do, we're going to put this full pattern on the top and the bottom. We're going to make a box. We're going to hollow it out. Okay. So we're going to put the full 8 bits on the top row and the bottom row. But all these middle rows, we're going to put a different pattern here. In fact, you know what I'm going to do? Instead of putting this hexadecimal, I'm going to do it in binary. So in binary, this is what I'm writing, which is all bits on. So that's just 8 solid things. Down here, I'm going to write a different pattern. That. So I'm going to turn on the pixels on the very edges. So now we should get a little box, an empty box. And there we go. So the player sprite, the graphics definitions are just pixels on or pixels off. 1 is on, 0 is off. Now, I think it's always helpful to see some real world examples. So here is Robin Banks. And you can look at some of the graphics data here. So here, this block right here is labeled player up 1. This is one of the facing up frames for the player in Robin Banks. And I like to put these in my code in binary form like this so I can actually see the pixels in the layout. Now, if you're not familiar with this game, you might not realize what you're looking at here. But if you go download the source code to this, you can go in here and play around with this. You can come in here, poke at these bits, change things around, and see how it affects the graphics, because it's all here. So we have this hat. There's a hat that starts up here, and there's a body. There's a little couple eyes. There's some feet. Yeah, it's tough to make out if you don't know what you're looking for. But look at the size of this thing. It's 16. It's 16 pixels tall, and of course, I mean, it's always 8 pixels wide. But it's that 8 by 16 shape, and this is the walking up frame. This is the second walking up frame. Here is the down frame 1, down frame 2, and so on. So I encourage you to go to my website, download the code to one of these games, and play around with these graphics. just to get a sense of how ANTIC represents the players. Okay, so that's a player. That's a player object. Now let's really have some fun. Let's move it around. So we need to kill the program here. So up until now, we've been configuring the system, setting everything up, and then just going to this jump start instruction, which just locks the system. It just puts into an endless loop, jumping back to itself. We're going to get smarter now. So I'm going to create a new subroutine here. I'm going to call it, if I can get my thing under control, I'm going to call it game loop. And this is, we're just going to fall into this. Now, before I do that, I'm going to write another subroutine here, which I have in all of my real projects, and it's called wait for VB. Oh, I was going to mention position 0, because that came up a little bit a while ago. So one unique thing about position 0 is that if a sprite is at horizontal position 0, it's guaranteed to be completely off screen. And the reason that's important, let me put that jump star back in here. I should show this while I'm thinking about it. Is that there's another interesting feature of sprites. They have 3 different widths. This is a normal width sprite we're looking at before. But there's a register called size P0. And if I write a 1 to size P0, that will give me a double width sprite. So if I look at this, it's going to be fat. So there's a double width sprite. Now it's still 8 pixels. The pixel just got fat. So now instead of 2 to 1, they're roughly 4 to 1. And there's even a quad width sprite. And I believe you need to write a 3 to that register to get the quad width sprite. There it is. That's the quad width sprite. Again, only 8 pixels. But they're really fat pixels. And you notice they're still really thin, though, because it's scan line by scan line. So you have 3 different sprite sizes. Now, each player object has its own size register, so you can make them all different sizes, depending on what your needs are. The missiles, there's one register that controls the size of all the missiles. So they're all or nothing. But quad width players, I think I've only used once. I think I was in my first game, Ratcatcher. I had these big alligators, and I made them with quad width players. I think I've used double width a few places. I think the wings on the characters in Magical Fairy Force are double width players. I think. You forget about these things after a while when you write enough of these games. But there's another interesting thing you can do with the players is change their size. But let's get back to what I was doing here. So I'm going to write this thing called wait for VB. So VB stands for vertical blank. So to go back to a little bit of television theory, when the TV has finished drawing the frame from top to bottom, it enters into a phase called the vertical blank. During the vertical blank, it resets the beam from the bottom of the screen to the top of the screen and waits for the signal to start drawing the next frame. The vertical blank is when you do most of your processing. So your timing is synced to the vertical blank. And so it's useful to have something like this. It's wait for vertical blank. So at the beginning of every frame, I wait for the vertical blank. So I'm just going to put this in here. So I always write this. And then I'll jump start. But at the beginning of every frame, no, I'm not going to jump start. I jump back to game loop. So this is closer to what an actual game loop will look like, except you would actually do things in it. But you wait for vertical blank, then you do all the work you need to do for the frame, and then you jump back and wait for the next vertical blank. Now, on an NTSC television, which is all the 5200 runs on, so you don't need to worry about it, this will get you 60 frames a second, because that's what the television display runs at. On a PAL system, it's 50 frames per second, and you need to compensate. But there is no PAL 5200, thank goodness, so we don't care about that. We only care about NTSC. I'm just now diving into the wonderful world of the 7800, which does have a PAL version, so I'm having to learn how to deal with that. But in the 5200, you don't care. You just don't care. But so we need a way to wait for the vertical blank so we can start processing without screwing anything up. And here's how you do that. If we go to hardware.s here, if you look at the page 0 locations, there's these two things right here, R clock high and R clock low. R clock stands for real-time clock. So one of the things that the vertical blank interrupt does, and this is a BIOS function that we set up to run somewhere up here. VBIN, vertical blank interrupt handler, is here. So VBIN is a location in the BIOS. So at the end of each frame, there's a vertical blank interrupt, which executes the code that we register there as the vertical blank interrupt, and that's in the BIOS. And the vertical blank interrupt in the BIOS does a bunch of bookkeeping stuff, and it's all very important. And one of the things that it does as part of its routine is it increments real-time clock low. And if that overflows, it increments real-time clock high. So there's a 16-bit frame clock right here at addresses 1 and 2. Now, I've never used this clock for any like actual timing purpose. The only thing I ever use it for is my wait for VB routine. Because here's how you do that. You load the low byte of the real-time clock. Did I spell that right? Yeah. Now, this is going to change on every vertical blank. So you load it, and then you start a loop, if I can type right today. Then you compare the value you just loaded to our clock low. And as long as it's equal, you go back to the loop. And then you return. So at the end of the frame, when the vertical blank period starts, the very first thing that happens is the vertical blank interrupt in the BIOS does its job. And part of its job is changing the value at our clock low. So as soon as it changes that value and we come back here, you're going to compare to it. You're going to see, oh, it has changed now, and return. So this is our wait for vertical blank. Now at this point, we should have a functioning game loop. So if I run this, it should do exactly what it did before. But this time it's not locked up. It's in the vertical blank loop. So let's make the game do something. Not really a game, but let's make it do something. So what we're going to do now is we're going to add a little bit of control. You know what? Not even, even before that, we're going to do something else. And up here, I always like to put these at the top. We're going to declare a variable. So these go, I'm going to put it on page 0. And we're going to call it, player X. And I'm going to put it at address hex 19. This is the first address on page 0 that you, the programmer, are allowed to mess with. So we got that right there, 19. Now right here where I write to hpos p0, right here, I'm also going to store that value to player X. Now, you need to store the player's coordinates independent of the horizontal position register because the horizontal position registers are write only. You can't read your value back out of them. In fact, I'm pretty sure they have a completely different purpose if you read from them. They do. If you read from it, you get a collision value. That's what this is. We'll talk about that later. But the horizontal position registers are all write only as far as you're concerned. So you need to have your own independent tracking of where your horizontal objects are. So with that being said, we now have that. This is where our object is. So here's what I'm going to do. Every time through the loop, I'm going to load player X, increment it, write it back, and also write it to hpos p0. So, what do you think is going to happen? There it goes. So, every frame, we're moving the player 1 pixel to the right. Now, eventually, that value is going to overflow, and it'll come back around from the left. But that's how easy it is to move a player object horizontally. You just write into the register, and you moved it. If this were a playfield object, like if we had embedded this into the playfield, then it would occupy very specific locations in memory within the playfield, which can be complicated to determine. And I would have to pick it up, move it somewhere else, fix the place it came from, like put something valid back there. It gets complicated. Sometimes that's what you got to do, though. But with the actual player and missile objects, moving them horizontally like this, easy, no problem. So here's what we're going to do to make this even fancier. We're going to control it with the joystick. For now, just left and right. Vertical movement is a bit trickier. And for the moment, we're not going to do it, but we could. Now, there are a number of steps you need to do to enable the joysticks. And I'm hoping I got them all here. But you know what? Even if I didn't, they'll still probably work because I mentioned this last week, and I will tell a funny story here because I can do that. Last week I mentioned that there are some aspects of the joystick control that a lot of emulators don't get right. In particular, there is a specific bit you need to set in this register right here, console. You need to turn on this bit in console in order to enable the joysticks to scan. And this emulator, among many others, does not do this correctly. And just a couple days ago, there was a post in the Atari 5200 forums at Atari Age of someone who was porting an Atari 800 game to the 5200, and they couldn't get their controllers working. They worked in all the emulators they tried except one, and it didn't work on real hardware. And the first thing I thought was, you didn't set that bit in console, did you? And it turned out that's what the problem was. So make sure you set that bit. So here's what we're going to do. Let's get rid of all of this. What we're going to do is we're going to look at the joystick. And if it's pushed to the right, we're going to move the object to the right. If it's pushed to the left, we're going to move it to the left. If it's neither of those things, we do nothing. So, how do you read the joysticks? Here we go. Getting into the infamous Atari 5200 analog joysticks. I forgot to bring my my prop with me. I'm going to go grab that real quick. I'll be right back. Okay, so here we are. Here it is, the infamous CX52, the 5200 analog joystick. Now, on the A8 computers, the Poke chip is equipped to read the paddle controllers, the 2600 paddles. And on the 5200, they use the exact same circuitry to read the 5200 joystick. So in effect, the stick is like two paddles. There's a horizontal paddle and a vertical paddle. So you read two values for this thing, a horizontal value and a vertical value. Now for the moment, we're only going to be concerned with the horizontal value. We'll get to the vertical value a bit. Vertical motion is tougher. We'll cover it. So let's go back to the hardware.s file and go down to Poke. So here's Poke. And we have these pot registers. They stand for potentiometer. These would be the paddle inputs on the Atari 800 and 400 and all those computers. But here they read the joysticks. But we're not going to read them directly from Poke. We're going to read them from page 0, where they have these things called pot shadows. So one of the things that the vertical blank interrupt does is it goes to Poke, triggers a read of all the joysticks, and puts all the values right here. So you generally don't read these directly from Poke. You read them from these locations on page 0. So we're going to be looking at Shadow Pot 0. This is the horizontal pot for player 1, the player 1 port on the console. And then pot 1 is the vertical pot. So we're going to be looking at the value in S pot 0 and using that value to determine whether we're going to move left, right, or not at all. So let's do it. So the first thing we do is we're going to load SPOT 0. Now, here's where things get a little bit tricky. So the range of motion on the joysticks, there's an official value, and then there's reality. And reality is that every stick is different. And this is one of the problems with the 5200 controllers, is that they don't have a lot of consistency. So you just need to kind of guess and get a good value. Now, I have found that the typical range of a controller is from 0 on the far left to about 220 on the far right. And that might actually be the maximum range. I'm not sure. But with that in mind, you can use 110 as a rough center position, but you need some dead space. Because the 5200 stick, infamously enough, it does not center itself. So you push over to the right, it pretty much stays over there. I mean, it comes back a little bit, but not much. So you need a dead zone in the middle where you're just going to ignore the value. And how big that dead zone is really depends on the game you're writing. Now, here I'm going to be using the keyboard to control it. So I effectively have a digital controller. So the size of the dead zone really isn't super relevant here, but we're going to do one anyway just to, just to do it. So my rule of thumb is use 110 as the middle. And we'll start by going, I don't know, 30 plus or minus, and we'll call that the dead zone. It's something to start with. So we're going to load the value. We're going to look at the, okay, so we loaded the value into the accumulator from ShadowPot 0. Now we're going to compare it to 110 minus 30, so 80. Compare it to 80. Now, if it's less than 80, we're going to move the square to the left. So we're going to use branch on carry clear, which would mean it was less, to a label we're going to call move left. Then we will compare to 110 plus 30, 140. Now, if it's greater than 140, we want to move right. But we're just going to shortcut this a little bit. And we're going to say if it's less than 140, branch back to the game loop and do nothing. So this is where we're going to put our move right code. And this is where we're going to put our move left code. So the move right code is real easy. Moving right, we're going to do it a different way. We're going to increment player X. And we're going to load it and write it to hpos p0. So increment is a very interesting instruction. It's one of the few instructions that can operate directly on memory. Typically, you need to load a value into a processor register before you can mess with it. Increment, decrement, and a small handful of other instructions, mostly the shifts and rotates, I think, are the only other ones, can operate directly on memory locations. So increment player X, and then we load it right as hpos p0. And then we jump back, if I can type, jump back to the game loop. Now move left is going to be similar, except we're going to dec player X. Then we'll load it right as hpos p0 and jump back to the game loop. So if we did this correctly, we should now be able to move the player left and right with the joystick. There's the player. Here we go. Right. There it goes. I let go. It stops. Left. There it goes. I let go. It stops. Check that out. Look at that. User input. Your first 5200 user input. We have a player object, moving it left, moving it right. How exciting is that? How exciting is that? That's just fantastic. This was the first thing I did on the 5200, and I was so happy about it. I don't remember what, I don't remember if I had a square, or I made something though, and I moved it left and right with the joystick, and I thought it was so cool. Like, look at what I'm doing. And then I went and I loaded it onto a cartridge I had at the time, put it into a real 5200, fired it up on my TV, didn't work. You know why? I forgot to set that bit. And the emulator I was using was perfectly fine with that. So yeah, remember to set that bit. There you go. Right, left. Look at that. Beautiful. We're moving the sprite with the joystick. Look how far we've come already. It's only day 2, and we're already moving a sprite. Now, I mentioned before, vertical movement is a bit trickier. Because vertical movement requires you to actually move the bytes through memory. Up and down. So it's trickier than horizontal movement. But before I get into vertical movement, I would like to do something else. And that is to talk about subpixel movement. So right now we're moving in whole pixels. We're moving 1 pixel a frame. Now, sometimes this is fine. Sometimes this is exactly what you want, but it doesn't give you a lot of granularity. Moving in only whole pixel increments, so you either move that fast or you move 2 per frame. Now you're going twice as fast. There's a lot of space in between there that you can't get if you're moving in whole pixel increments. And similarly, going the other way, you could move every other frame. That's going to cut your speed in half, but there's a lot of space in between there. You just kind of lose. So in a real application, you're typically going to do this in terms of subpixels. So what you're going to do is you're going to have player X. Well, actually, I'm going to put player sub X. Change this to player sub X. And then we'll have player X will be the next address. And then we're going to have a constant. We're going to call it player speed. Which will make it, oh, I don't know. $100. So here's what we're going to do instead, which is really a much smarter way to do it. What we're going to do is every time, when you move right, we're going to add player speed to player sub X. And if it overflows, which means it goes over 255, we're going to add 1 to player X and move the player. So now you're going to move right every roughly 2.5 frames. So it'll be slower. But this allows you to get much more fine-grained movement instead of having to move in whole pixel steps. Because you can't really do much with that. So let's change this code a little bit to get subpixel movement. So we'll start with move left since it's conveniently labeled. So we're going to be doing this a different way. So what we're going to do, and this demonstrates addition too. We're going to load player sub X. Now we're going to clear the carry bit. You typically need to do this before you do an addition. Although, you know what? In this case, we don't need to. Okay, so this is assembly tricks here. We're getting into assembly hacks. So typically you need to clear the carry bit before you do addition. And the reason for that is because when you add 2 numbers, the carry bit gets added to it, because that's how you do carrying for bigger math, for like greater than 8-bit math. But look at this label, move left. How did we get to move left? Branch on carry clear. So if we were at move left, we already know the carry bit is clear. So we don't need to do it again. That's a waste of an instruction and a waste of 2 cycles. So you know what? We're not going to do it. Instead, we're going to add player speed. And I need to use a little number sign there because this is a literal number. If you don't put that there, then it interprets it as a memory address. Now I'm going to put a note here. Carry is clear. Whenever you do this, you probably want to put that note there, just so you know, carry is clear. Now, if the carry bit is set at this point, it means we've overflowed the subpixel value, so we need to update the main value. So if we can just branch, right now we can just branch on carry clear to game loop and say, you know, at that point we're done. But if carry isn't clear, it means that we looped. So we need to increment player. Okay, I should have left that in. Increment player X. And then write it to hpos_p0. I feel like there are better ways to do this, but I don't feel like getting crazy optimizing here at the moment. Now, for the move right case, we're going to do the other option. And look at this here. Okay, so we're going to leave. Oh, no, move left is an increment. I'm sorry, this is backwards. Oh yeah, okay. So this little trick's going to go away because I did this backwards. So moving left, we're going to subtract. So to subtract, we have to set the carry bit, which we know we need to set because of that. And then we're going to subtract player speed. But you know, we could get real fancy here too. Since we know for a fact the carry bit is clear, we could actually modify player speed. We could like do player speed +1, or is it -1? I think it's +1. And if you were really super optimizing, you would do that sort of thing, but we're not going to do that. So if we subtract and the carry is still set, we didn't underflow. So we're not going to update the thing. So there's deck. There we go. We're done. So up here is where we're going to do the adding. I screwed that up. So, and again, if we're here, we know carry is set. So we could do some fancy optimization here, but this, for the sake of clarity, I'm not going to do that. We'll do the proper way to do this. But yeah, as an assembly programmer, you do need to know some of these tricks. Eventually. Oh, you know what? I forgot to update player X. Update player sub X. Before we go branching there, we need to update player sub X. We need to write the value back. All right, so this should get a subpixel movement unless I've screwed something up. Okay, see now look, it's moving much more slowly. And that is a movement rate that you can't get if you're moving in whole pixel increments. So now we can just go in and play with that speed value. And we can get a whole range of speeds instead of 1 or 2 or 4, which just keeps getting bigger and bigger and bigger. So subpixel movement is usually something you want because it just gives you much better movement. And not to mention things like acceleration, stuff like that. And especially with this analog stick, right? I mean, if you're going to do something that actually makes use of analog control, you know, you want that range of speed. You want to be able to, you know, to have that sort of level. So now we can go up here. We can change that player's speed value. It was 100. We'll make it 200. So now player's instantly twice as fast. We just changed the variable, changed the speed value, and now it's twice as fast. But it's still moving less than 1 pixel every frame. It's moving a pixel. Some frames it's not going to move. But this gives us much smoother speed. So subpixel movement is something you almost always want. So sometimes you don't. Sometimes you're fine with 1 pixel at a time movement. But yeah, subpixel movement is usually the way to go. Now, I don't know if I necessarily want to jump into vertical movement here, because vertical movement is tough. Real tough. And I don't plan on using vertical movement, at least initially, for the game I have in mind. And if we're going to do vertical movement, we're going to need to write some support routines to kind of back it up and to help out with that. I'm not sure I want to do that quite yet. But on the other hand, I'm not sure what else I would do. Actually, I think I know what we can do. So let's have a little bit of fun here. Since we looked at the joystick, we did horizontal movement. Now, the vertical pot is pot 1. You know what? Let's do vertical movement. All right, so here's how we're going to do this. The first thing I'm going to do is I'm going to move the player's graphics data to a memory locator, to like a block somewhere that I can copy. So we'll call it player sprite. And the player sprite looked like, right now it's the box. Oh, we'll probably change it in the long run. So we had solid 8 bits. And then 14 rows of this. Whoops. What is going on? Vim, I love you, but sometimes you're just nuts. All right. And then this. All right, so this is our player data. It's just that box. So what we're going to do is we're going to write a subroutine. Actually, you know what I'm going to do? I'm going to put a blank byte on the top and the bottom, and there's a good reason for that. Okay. So, here's what we're going to do. We're going to create a subroutine called draw player. And it's going to draw the player on its page, which is page hex 14, starting at the offset in the Y register. So here's what we'll do. We need to know how many bytes we're going to draw. It's going to be 18 bytes because I padded it with zeros, which will be important. And then we're going to go into a loop. Actually, I want this to be 17. So here's what we do. We load player sprite. That's the address of all that data. Indexed by... Actually, I need to start at 0. or it'll be upside down, indexed by X. So this is the first, so the first time through the loop, we're loading the first byte, and then we're writing it to the player's data page, which is 1400, indexed by Y. So we're putting it there. Then we're going to increment X. No, actually, first we'll increment Y. No, increment X. Actually, no, we'll do it this way. We'll compare X to, well, how big is it now? It's 8 to 17. So if X is 17, we just wrote the last byte. So if X equals 17, we're going to branch out to a label called done. If it doesn't equal 17, we increment X, increment Y, jump back to loop, do it again. And then done, return from subroutine. So now we have something that will just draw this player data at the location of Y. And I mentioned earlier, the way to think about the vertical position of the sprite is that address, that base byte in its page. That's the vertical position. That's the way I think about it. So we're going to replace this garbage here. So I started drawing this at what address? 1480. So now we have a function that can draw the player. So what we're going to do is we'll load Y with 80. That's where we want to put it. And then we're going to jump to subroutine, draw player. So this should now get us right back to where we were before, but now we have this convenient subroutine that can draw the player. Actually, you know what? This is going to be off by 1 because I put those buffers in there. And what happened? Okay, we screwed something up. Okay, let's see. So load Y, number $80, fine, draw player. All right, so draw player. Let's look what we did wrong here. Oh, I put number 9. It's supposed to be number, I don't know how I got a 9 there. It's supposed to be 17. No, it's supposed to be 0. I accidentally put 9. Yeah, whoops. Yeah, that'll screw it up. Okay, there it is. So we're just writing this a different way now. It's actually 1 pixel lower than it was before because I put that 0 in the buffer at the top. And I'll show you why I did that when we start doing vertical movement. So what I'm going to do now is we're going to set up a similar thing for player Y. First thing I'm going to do is I'm going to change this variable to player X speed. And wherever we do player speed, and change that to X speed. So this is one of the issues with this system, which goes back to the fact that pixels are wider than they are tall. So you need to use different speeds for vertical and horizontal movement. And again, the ratio is roughly 2 to 1. So I usually make the vertical speed twice the horizontal speed. However, in this case, that is a bit of a problem, isn't it? Ooh, no. Actually, I have a clever way we can do this, I think. I take it back. I'm going to try this. I just got an idea, and I've never done this before, but something just occurred to me. I'm going to see if this actually works. So we're going to, here we go. Player sub Y equals 1B, and player Y equals 1C. So I have an idea. Now we need to set the initial value of player Y. So that's this value here. So we'll write that there. Okay, so here's what we're going to do for vertical movement. And I don't know if this is going to work, but it's going to be fun to try it. And if it doesn't work, I'll explain why it didn't. Okay, so we check pot 0 for left and right. Now here, instead of branching to game loop, this is the case where the joystick's in the dead zone horizontally. Instead, we're going to branch to a label called check vertical. Here as well, we're going to branch to check vertical. And again to check vertical. I hadn't anticipated doing vertical movement tonight, but we'll run with it. Why not? Okay. So here's check vertical. All right, so Now, the reason we need to do this is because the two axes are independent. Whether or not there's horizontal movement doesn't matter. We still need to check the vertical. And the vertical is pot 1. So we're going to apply the same test to pot 1. We'll use the same dead zone. Compare it to 80. Now, below 80 is going to be up, I think. I hope. If we're wrong, it'll be immediately obvious, and I can just reverse the logic. I think it's up. Now here, okay, so if this test fails, we're in the dead zone. I'm going to jump to a label called move done, which I'm going to put right here. Because eventually we're going to have some game logic, and that's probably where it's going to go. All right, so I typed move down, didn't I? Move done. Not to be confused with move down. Okay, so this is where the move down is going to go. And then here's the move up. So, how do we move up? Well, it's just like moving left, except we're doing it on sub Y. So we look at move left. Load player sub Y. Set the carry bit. Subtract player speed. Now, here's where it's going to get tricky. I don't think this is going to work the way I want it to. You know what I think we're going to do? For the moment, we're going to ignore the fact that vertical movement is going to be only half the rate of horizontal movement. Yeah, we're just going to ignore it for now. We can fix it later. It's supposed to be sub Y, not sub X. All right, so if carry is set, we branch to move done. Otherwise, we decrement player Y. Now, here, there's no register to write to. So we're going to load player Y and then JSR to draw player. And then we're done. Now up here, we do it the other way. And there are a lot of ways this code could be optimized to save space, but I'm not super concerned with that right now. I think I'm doing this right. Okay, so if I did this right, and I'm not sure I did, we should now have vertical movement, but it's going to be real slow relative to horizontal movement. Ah! What am I typing? I don't even know what I'm typing here. Okay, so horizontal movement still works. Now we push up. Look at that, moving up and down, moving down. So we got the movement, but it's slow. Here's the diagonal. We can do both at once. But vertical movement is very slow. I mean, you can see the angles here, maybe. Yeah, vertical movement is slower than horizontal. But there it is. So there's a sprite moving all four directions. So as you can see, vertical movement is a much more complicated thing. Now I want to go back a bit here. No, actually, let me bring the window back up. So I want to talk about why I padded the sprite data with zeros on the top and the bottom. So I added this extra 0 on the top and 0 on the bottom. And the reason I did that was because that conveniently erases what's left behind of the old sprite position, as long as you're only moving it 1 byte at a time. So if you think about it, if you imagine writing this again, but starting like 1 pixel higher, if I didn't have the 0 here, it would leave this behind. This would still be in memory, this last row, if I moved it up. So I just leave a trail behind me. But by making the last thing this 0, the last byte that clobbers the original one of these. So by padding with zeros on top and bottom, you erase the old image just by moving up and down, if that makes sense. You might need to work it out on paper to see why this works. But this is how I generally do vertical motion on my sprites. Sometimes I don't. It depends on the circumstances, but this is usually the way I do it. In fact, let me actually demonstrate. We'll take it away. We'll show what would happen if I didn't have that there. So what we'll do is, actually, let's change these to all ones. So let's have a thick border. So if I don't make those zeros, I'm going to make them all ones. You'll see the results. All right. So this is still the same, but now when I move up, see, it leaves all that behind. Having that extra 0 on the bottom erases the previous bottom line. And moving down, same thing. It's leaving that on the top. That's kind of a neat effect, but it's not really what we want. Now, it is important to note that running off the top and the bottom, I'm not sure if it's going to loop. I mean, vertical move, I'm not going to try it, but vertical movement is just inherently different from horizontal movement. So you can't really assume that the same rules apply to it. But we now have a free roaming sprite. And we can move this thing. It's there. The joystick would move this. If we plug this into a real 5200, this thing would move around. No problem. Now we do need to solve the vertical movement speed issue. And there are ways to do that. But for the moment, I'm not really concerned with it. It's just cool. I mean, look at this. I mean, isn't that cool? You're making that. And look at that. It's transparent. That's an important thing, too. The empty spots on the player objects are transparent. So you can see the playfield through them. Now, one register I haven't talked about yet, there's a register called Prior. I believe it's in GT. There it is. Prior. It stands for priority. So there are a variety of sprite priorities you can set. And not every possibility is covered, but you can find a chart for this on Wikipedia. And it mostly concerns the playfield. So the playfield has several colors. We haven't really seen colored playfield or anything like that yet, but we will eventually. And you can have different playfield colors appear in front of or behind certain sprites. So you have different layering options here. Right now we just have default priority, which is, I think all the players are on top of all of the playfield stuff. Although here you can't tell because they have the same color. But if that text were a different color, I'm pretty sure the player would take priority. So let's, or if the player is a different color, let's make the player a different color. Where is that? I'm going to find all this stuff now. There we go. S color player missile 0. So we'll make the player, I don't know, what color we want. We'll put 2A. I don't even know what color that is. 3A. I have no idea what color this is, but that's the color we're going to make the player. Okay, so it's some kind of whatever color that is. And you can see here, this color appears on top of the playfield because of the way the priorities are set up. There's probably a priority that reverses this, and the player would appear to be underneath those letters. But I don't feel like digging through the priority chart to find it right now. But there you go. There's a fully roaming player object. Now, I'm not sure if we're going to really use vertical motion in the game I have in mind, but I mean, we implemented it, so maybe I will. So what I had in mind for the game I was going to do here was a simple kind of demon attack-like game. I was imagining the player at the bottom of the playfield shooting up at some few objects flying near the top. But maybe we'll give the player vertical motion. Maybe we'll let you go up and down a little bit, like Centipede. I mean, we got the stuff now, right? And you know, we could even leave the speed the way it is. We could have the slower speed moving up and down. It could be a feature. Maybe we could put gravity in. There's a lot of stuff we could do. But, all right, so we got a player moving. Now, I want to talk a little bit more about some of the other playfield modes because I think these are important. So let's do that. So far, I've shown you mode 2, which is, this is a text, 40-column text. There are some other text modes, some of which are very interesting, but I don't want to talk about those. What I do want to talk about are some of the bitmap modes. So what I'm going to do is instead, I'm going to change this to mode E. So mode E is 160 pixel wide, 4-color bitmap. This is probably the graphics mode that gives you the most freedom, but it also occupies a lot of memory, and it's difficult to manipulate. It's good for static images, but it can be difficult to move things around on it. Now, this is just one row of mode E, which one mode line of mode 2 was eight scan lines high. It was a whole line of text. One mode line of mode E is one scan line. It's barely anything. So we're going to put some more mode E lines in. Let's put in about, I don't know, 15 more. All right, so now we got 15 lines of mode E. So I want to do now is put kind of an image, a mode E image. So where did I do that text draw? Okay, we're going to get rid of this text loop. We're not doing this anymore. All right, now here's where I was setting up colors. We're gonna get rid of the playfield color stuff we were doing. We'll leave that. We'll leave the background color the way it is. Okay, so mode E is 4-color bitmap. So this allows you to do some really detailed stuff. So we're just going to come up with a sample of this. Now this is a bit harder to visualize. So the format of the graphics here is every byte has color data for four playfield pixels. So it's 2 bits per pixel. And there's 4 colors available. So bit pattern 00 means the background color, in this case black. And then bit pattern 01 is playfield color 0. Unfortunately, it's a little confusing. Bit pattern 10 is playfield color 2, and 11 is playfield color 3. So this single byte here would get us all 4 playfield colors in one byte. So let's call this, I don't know, background. Maybe we'll design a fancy background. Maybe I'll come up with one at some point and we'll put it in. But we'll call this background. And I'm just gonna repeat this a few times here in the setup. Although I need to set up some actual colors. So let's see what we can do here. Let's do color 1A. And we'll write it to, that's not a 1, is it? We'll write it to that color 0. This is playfield color 0. I'll put should be that I can't type today. I blame it on being still somewhat sick. Okay, we'll do 2A to color 1 and 3A to color 2. And then I'm going to load that background byte. I'm going to write it to address 2000 because we're still displaying the data at address 2000. We're just interpreting it differently now. Now it's being interpreted as a bitmap instead of text data. So let's see what we get here. All right, so it's tough to see, and I seem to have screwed up the player color along the way, but there are some pixels there. And, you know, it's really tough to see. So I think we're going to do this a little bit differently. Here's what I'm going to do. There's some more bytes here. So we're going to do the first byte of the background is going to be all zeros, which is going to be the background color. And then we're going to have the second byte is going to be all color 1. So it'll be 0, 1, 0, 1, 0, 1, 0, 1. That's 4 pixels of color 1. And then the next byte will be 4 pixels of color 2. So it'll be 1, 0, 1, 0, 1, 0, 1, 0. Did I put a dollar sign there? It needs to be a percent sign for binary. And I put 9s in there. Geez, I can't see today. And then the last byte will be 4 pixels of color, the last color. So I'm going to put 4 different ones in there, and hopefully it'll be a little more visible this time. So where did I do that at? All right, so background will go at 2000. Background plus 1 will go at 2001. Background plus 2 will go at 2002. And then background plus 3 will go at 2003. All right, so let's see if that works. Okay, so all right, you can those colors are too similar, unfortunately. Yeah, I need to pick some better colors. They're just too similar. I'm having trouble seeing those. I also don't know what happened to the player 0 sprite. I'm going to figure that out too. And my cat's yelling at me for some reason. Oh, I never wrote the H-pause, did I? Oh. Yeah, okay. All right, let's find some better colors here. So, oh, it's C. I like that. We'll do C, CA. And 5A. We get some purple. Okay, let's see what that looks like. Maybe it'll be a little more visible. Okay, yeah, that's better. All right, so you can see there's 3 different colors there. And it's indented in a little bit, even though that's kind of tough to tell, because that first byte was all background color. But you see, now we have those are 3 pixels wide. So again, the pixels are roughly twice as wide as they are tall. So you know what I think I'm going to do to make this a little bit more visible is I'm going to put a few more rows in there. Because we have, what was it, like 15, 16 rows of mode E here. So we're going to put some more rows in here. So each row is 40 bytes. And 40 bytes is 28 in hex. So we're going to write the same pattern to 2028. 2029. 202A. And 202B. So that'll make them now 2 scan lines thick. So these should be a little bit easier to see. Yeah, okay, much better. Yeah, so you can see 3 different colors there. So now we have this, well, you have the background color too. So we have this 4-color playfield that we can mess with. And you can create some fairly detailed images with this. So it's 160 pixels wide. And the visible area on an NTSC is 192 scan lines. So basically 160 by 192. So I'll give you an example of ways you can use this. So I'm going to go to one of my older games, which I haven't run in a while. Whoops. Where's my run script? All right, maybe I didn't use the run script at this point. Okay, I'm going to do this the hard way. No, you know what? No, I can do it this way. I can use a different emulator. No, it's not going to show up. Okay, I'm going to try this once. If it doesn't work, I'm going to do something different. There we go. Okay, so this is Magical Fairy Force, one of my older games. And these characters, portraits here are done in mode E. So this is the 3-color mode. You can see you can do some pretty detailed stuff here. Now I'm doing some other tricks here involving scanline interrupts to get a few more colors in there. But this is what you can do with this graphics mode if you know what you're doing. And in fact, I think everything on this screen just about is mode E, actually. So there's lots of mode E going on here. It's a great graphics mode. Unfortunately, it does take up a lot of space. But that's fine. In fact, these character images originally took up, how much was it? 8 kilobytes? Yeah, it was roughly 1 kilobyte per image. Because I needed the image data itself and a color table and all this other stuff, which is about 1/4 of the cartridge size. I ended up having to compress them. You can actually see them draw in a little bit when you go down. You can see them kind of fill in because it takes me a while to decompress the data and write it to memory. And that is a big problem with mode E, is that manipulating mode E is very slow because you have to do a byte for every 4 pixels. Now, I don't have it here, but in the 2-player mode, the same image appears up top, but it's reversed horizontally. It's mirrored. And I had to do that on the fly. So that one draws in even slower because it's mirroring it in real time, which is an unfortunate consequence of where I ended up. But this is the sort of stuff you can do with mode E if you have the data. You know, it's hard to assemble the data. I'll probably try to put something together before next week. Maybe some kind of a simple background we can use in mode E to display it. God, I don't even remember how to play this game now. But yeah, I mean, this is almost all mode E. And a significant portion of this screen is mode E as well. But anyway, just wanted to show that off. Because mode E has a lot of possibilities. But it's definitely best for static images. You know, it's the sort of stuff you're going to set once and just leave there. It's even better if you can display what you want to display directly out of the cartridge. But you can't always arrange that. Sometimes you can. Robin Banks, for example, does that. The title logo on Robin Banks is actually displayed straight out of the cartridge, so I don't need to copy it into memory or anything. But that's an issue for another time. Okay, so what do we have here? What have we accomplished here today? We have a sprite. We can move it with the joystick. We got Playfield Mode E going on up there just as kind of a demonstration. Now, I think what I'm going to do, and I'm not sure I'm going to do it today. In fact, I might be getting about ready to cut this video off because I think I'm going to have to do a lot of prep work for the next one. What I want to do is I want to create like a ground down here, like a sort of a, kind of like in Space Invaders, I see on 2600, you see the ground at the bottom. I want to prepare something like that. So I have some kind of a ground for here for the player to sit on. And I might design some simple sprites, like some enemies and a player or something like that. You know, just so we have more than just a box and some stuff. But you see here the Playfield Priorities. Is this? Yeah, this is priority over all those colors. There would be at least when I was talking about colors. So in that priority register, there would be a setting where this sprite would appear behind certain colors on the playfield if I dug into the priorities and set that up. But I'm not going to look that up right now. We might mess with that later. But yeah, I think this might actually be a good place to call this video done for now, because we've gotten the system working. We fixed last week's problems. We got a sprite on the screen moving around with a joystick, and just did a little bit of sample playfield stuff. So I think before next week's show, I will prepare some stuff. I'll try to have some kind of a simple playfield that I can show off that we can use, and you know, we'll go from there, and we'll see what we can do. Maybe I'll do like a star field with just like a nice ground for the player to sit on. So I think we'll put the player down here. We'll have some things flying around up top, and we'll work on getting the player to shoot. And I think that'll be probably the next thing we do too. But yeah, I think that's probably enough for today. You know, we've gotten some good stuff done. And I'll probably post this video to YouTube within a couple of days once I get it downloaded and processed, probably sometime tomorrow. And next week I will do some advanced planning and have some stuff ready. And we'll take this sprite and actually turn it into something useful. So tune in next week to see that. And again, if you missed this or didn't get to see all of it, it should be up on YouTube probably tomorrow. You can fill in the blanks. And we'll see you next week and get a step closer to having something that kind of resembles a game. And hopefully by the end of next week, we'll have that. So we'll see you then.